Hello everyone, welcome to this video on the prerequisite of a Laplace transform. These are the prerequisite formulas of a Laplace transform. So before you start this topic, Laplace transform, you must know these 27 formulas. Then it will be easy for you to solve the numericals on the Laplace transform. So out of that 27 formulas, 7 are trigonometric identities, 7 are integration formulae, 4 formulas are from differentiation, 1 formula is of a limit, then definition of a gamma function, and some 2-3 properties of a gamma function. And lastly, you must know the partial fraction method. So that about the prerequisite formulas. We'll see these prerequisite formulas one by one in this video. So the first set is from the trigonometric identities. These trigonometric identities mainly we require to convert the multiplication of a trigonometry, see the multiplication of trigonometry in terms of the addition of trigonometric function. So we convert multiplication to the addition so that easily we can get the Laplace transform by using a standard result. So you must know, you should know this formula is here, but before we proceed here, I suggest you should take a pause for the video and you should take a pen and paper and you should write on the paper these formulas. If you are able to recall it, it's a good thing. Otherwise, just continue the video, go through the formulae once, and then at the second time, you should able to write it without looking the final answers. Okay, so take a pause and write it on the paper first. If not, continue it. Okay, I will start with the formula number 5, which is sine A cos B. Sine A cos B can be written in terms of addition is 1 by 2 times sine of A plus B plus sine of A minus B. Okay, then cos A cos B is written as 1 by 2 times cos of A plus B plus cos of A minus B. And the last one, sin A sin B, is given by 1 by 2 times. Now here is a different cos of A minus B minus of cos of A plus B. So these three formulas are similar to each other. Remember, on the RHS there is only sine, only cosine, or only cosine. There means same function is there, so we are adding or subtracting the same function. So this way we get the multiplication of sine into cosine, or cos into cosine into cosine, or sine into sine there in terms of the addition. Okay, so that about the first three formulas. Next two are, say, cos square theta and sine square theta. They are the particular case of this formula 6th and 7th. If you want cos square theta, just replace a and b by theta only. So we get cos theta into cos theta, that is cos square theta is 1 by 2 times cos of theta plus theta is cos 2 theta, and here cos 0 is 1. So we get a formula as 1 by 2 times 1 plus cos 2 theta. Similarly, we get a formula for sine square theta from the 7th as 1 by 2 times 1 minus cos 2 theta. You can directly remember, no need to derive it. Okay, and lastly, the two formulas are there. Actually, for that you should know the triple angle formulae. Say sine 3 theta. Sine 3 theta is 3 sine theta minus 4 sine cube theta, and from this we can get the formula. We can get a formula for sine cube theta, and that formula is 1 by 4 times 3 sine theta minus sine 3 theta, and that about a formula for sine cube theta. And lastly, we have cos cube theta. For that, you should know the formula for cos 3 theta first. Cos 3 theta is a 4 cos cube theta minus 3 cos theta. The first important thing you will observe in triple angle formulae everywhere the same function is there. The sine is there in sine 3 theta formula, and cosine function is there in cos 3 theta everywhere. And in each term, 3 appeared there, either in the suffix form or in the power form. So that can be used to get these cubic formulas. And here we have cos cube theta. Cos cube theta becomes 1 by 4 times cos 3 theta plus 3 cos theta. Cos 3 theta plus 3 cos theta. So that about the 7 important trigonometric identities that you require for the Laplace. Okay, so that is the first set. Now let me move to the next set here. The next set is the 7 important formulas from integration here. For integration, yes, again take a small pause, complete it, otherwise you can continue. So remember these formulas you require in taking the first of all, when you have to find the Laplace by using a definition of Laplace. Next, if you have to solve the numerical by using a Laplace, or you have to derive the standard results of Laplace, and lastly, the periodic function. So at 3 places mainly you require this integration formula. So come to the formulas here. The first one is e raised to x, the simplest formula. Integral of e raised to ax is e raised to ax upon a. The common silly mistake I observe generally that many students confuse with derivative and integration formulae. So remember, in integration, every time you have to divide by the coefficient, and in integration you have to divide by the coefficient, while in differentiation you multiply. So e raised to x upon a should be there, not into a. So this is the first formula. Now integration of x raised to n is x raised to n plus 1 upon n plus 1 on n plus 1 plus c. That's the second. Integral of 1 upon x square plus a square. This is 1 by a tan inverse of x upon a plus c. Next, fourth and fifth are the most important formulas. These formulas require number of times. Actually, these are the particular case of the biparts only. These are the example of biparts, but you have to remember now this is like a formula. So the formula is e raised to ax upon a square plus b square, then a sine bx minus b cos of bx. And similarly, the formula for e raised to x into cos bx is e raised to ax upon a square plus b square a cos bx plus b sine bx. So these are two important formulas which are actually require in some other topics like Fourier also number of times. So remember these two formulas. Sixth formula is integral of f dash x upon fx. It is actually a substitution method. If you put fx equal to t, you get f dash x dx as a dt. So integral of dt upon t is a log t. So the formula becomes log of fx plus c. And lastly, the bipart formula. This is the integration bipart. First into integral of second minus integral of derivative of first into integral of second. So this about the last formula. Obviously, the concept of integrations are there in all these formulas. So that about the 7 integration formulas you should remember. So we'll move to the next set then. Third set. Third set is just this, not 3. These are four differentiation formulas. We should know these 4 differentiation formulae. First is derivative of x raised to n is n into x raised to n minus 1. Now you will observe n is multiplied here. In differentiation, there is multiplication. Derivative of 1 by x. Common silly mistake. Many of the students write log x only. Remember, integration of 1 by x is log x. Derivative of 1 by x is minus 1 upon x square. It is actually a particular case of the first result only, where n is a minus 1. Then quotient rule, rarely required. Denominator into derivative of numerator. minus numerator into derivative of denominator upon a denominator square. And lastly, derivative of log x is 1 by x. All these differentiation formulae we require actually while taking the inverse Laplace by derivative property. Inverse Laplace by derivative property. That time we require this differentiation formulae. Come to the next then. Limit and gamma function formulae. Okay, every time I will suggest you to pause the video and try to finish it your own first. If you are able to do that, that's a good thing. Otherwise, you go through the formulas and then later on you should write it on the paper. There is no shortcut. When you write on the paper, then only you can able to remember this formula. Okay, the first formula is of a limit here, limit of sine t upon t as t tends to 0. So this formula we require in only one example of Laplace, and this limiting value is 1. And this value 1 can be proved easily by a L'Hospital rule. I'll not go in the derivation. Next, definition of a gamma. Gamma of n is defined as integral 0 to infinity e raised to minus x raised to n minus 1 dx. Now, where we require this gamma function definition, actually to prove the standard result, to prove the standard result of a Laplace of algebraic function, we require this definition. Only one place we require this definition. But yes, the properties we require, whatever the properties that we have, that properties we required in numericals. The first property is gamma n plus 1. Gamma n plus 1 is given as n gamma n, provided n is a fraction. N is a fraction. If n is a fraction, gamma n plus 1 is written as n gamma n. And gamma n plus 1 is given as n factorial if n is an integer. N is integer. So this property is important that we require in numericals mainly. And last two values, gamma 1 is 1, gamma half is root phi, gamma half is root phi there. So these properties you must know for the Laplace there. Next thing then, now this is the last part of the video actually, where you should know the 4 types of a partial fraction method. And mainly this partial fraction method we require for taking the inverse Laplace only, inverse Laplace of obviously the fraction inverse Laplace when we have algebraic function and where we have the we have fraction actually, and we have say proper fraction first, where the degree of denominator is greater than the numerator, and we have denominator can be factorized in the either in linear or quadratic factors, and we require that inverse Laplace of that. So it is exactly same thing that we you face in the integration when you have to find the integration of when you have to find the integration of say this one. Suppose you have to find the integration of 1 upon x plus a into x plus b. You don't have direct formula for this integration. What you do it, you write it in the partial fraction form, a upon x plus a plus b upon x plus b, and you find out the values of these constant capital A and capital B, and then you can easily integrate and you get the answer as a times log of x plus a plus b times log of x plus b. So the whatever the purpose that we have in integration, the same purpose is here in the Laplace. In the Laplace also we don't have the Laplace of this type of the term, so we convert it in the form of 1 upon linear term plus b upon the linear term, and then we can take inverse Laplace easily. So at the time of inverse Laplace, you will require this partial fraction method there. Okay, so which 4 types are there in the partial fraction? So first is when we have these linear and distinct factors in the denominator. That is the first thing. Then we have linear repeated factor in the denominator, linear quadratic factor in the denominator, and the last one when only quadratic term is there, nowhere linear term is there. There is no linear term, only quadratic term. So these are the 4 different types of a partial fraction that we have. We'll see these one by one. So here we have these 4 different types there. You'll observe the case 1. case 1 is there, where linear factors in the denominator, and you know how to write the partial fraction for this is like a upon s plus a plus b upon s plus b. Whenever there is a repeated factor, remember, whenever there is a repeated factor, there is extra constant for that repeated factor. So partial fraction of the second term will be a upon s plus a plus b upon s plus a square plus c upon s plus b. So first thing, you should be able to write the correct partial fraction. Then we have quadratic factor and the linear factor. So in such a case, yes, you can write like this. The linear term should be in the numerator for quadratic term. So quadratic term is s square plus a. So numerator of s square plus a is as plus b. Now this is a linear term, so only one constant is enough for that. So c upon s plus b. And lastly, when everywhere is a quadratic term, you can treat like the case 1 only, this case 1 only, where you replace s square by x there, and you can take a simple partial fraction a upon s square plus a plus b upon s square plus b. Remember, in this case, if you start with this one, as plus b upon s square plus a and cs plus d upon s square plus b. If you start with that, so automatically what happens? Automatically this will happen that the value of a will go to the 0, the value of c will go to the 0, because throughout this fraction only quadratic terms are there. So coefficients of linear term automatically become 0, and you're left with b upon s square plus a plus d upon s square plus b. This simple fraction there. Okay, that way. So there is no need to take as plus b and cs plus d when everywhere quadratic term is there. Okay. So that about the different types of a partial fraction. Now quickly, these are some of all these here only, but I will show you example of each case separately here. So come to the first case, case number 1, when we have linear and distinct factor. Suppose we have linear and distinct factor. We'll do it with one example. So I will write the example first. Say we have s upon s plus 1 into s plus 3. S upon s plus 1 into s plus 3. So the partial fraction, yes, we already seen here, a upon s plus 1 plus b upon s plus 3. There are multiple methods to get the values of a and b. The mainly equating the coefficient by substitution, and third is a shortcut method. I will show you the two methods here, which is a substitution method and shortcut method, and generally that are useful only. Why I am not showing this equating the coefficient? Because it's a lengthy method. First we get some equation in the constant capital A and B, and then we have to solve that equation simultaneously to get AB. So the first method is a substitution method. So in the substitution method, first we have to cross multiply this fraction. So cross multiplying s plus 1 into s plus 3 on the both side, we get s is equal to a times s plus 3 plus b times s plus 1. Now to get the value of a, yes, we should put that s equal to minus 1. We have to make the other coefficient, other term as a 0. So this equation is valid for infinitely many values of s. So the simplest or the best value is s is minus 1. If we put s equal to minus 1, what happens? We get minus 1 is equal to a times minus 1 plus 3 is a 2, and this is minus 1 plus 1 is 0. So b is a 0. So we get a directly. So what is a? A becomes minus 1 by 2. Now if we put s is equal to minus 3, so that we can make the coefficient of a as a 0. So we get minus 3 is equal to b times minus 3 plus 1. Minus 3 plus 1 is a minus 2. So we get the value of b as 3 by 2. And we can easily replace these values of a and b in this original fraction, and we can find integration, or we can find the Laplace of that. Okay, inverse Laplace of that, sorry. So that about substitution method for getting the constants of the partial fraction. But the shortcut method is actually derived from this substitution method only. What we are doing in the shortcut method, suppose we are interested to get the value of a. To get the value of a, we write this given fraction only, ignoring this denominator of the coefficient a. So just ignore s plus 1 term in the given fraction and write down the remaining. So we left with s upon s plus 3. S upon s plus 3, and then we put s is equal to, in this we put s equal to the value by equating the denominator of a to the 0. So we put s plus 1 is a 0, so s is a minus 1, so we put s is a minus 1. Now you will observe, put s is equal to minus 1, we get minus 1 divided by minus 1 plus 3. Minus 1 plus 3 is a 2, so we get the value of a, which is the same as a minus half. You will observe same. To get the value of a b, we do the same thing. Just we ignore this s plus 3 from the given fraction and we write down the remaining. So ignore s plus 3 factor, write down s upon s plus 1, and by putting s is equal to, equate the denominator to the 0, s equal to minus 3. So s plus 3 is 0, so s is a minus 3. So minus 3 upon minus 2, which is a 3 by 2. And that's the same value of a b there. So this is the shortcut method. So you can use a shortcut method also in the exam. The main purpose, the main thing is you should able to get the values of this constant. Okay, once you get the constant, you can easily find the inverse Laplace, and that we'll see while solving the example of inverse Laplace there. So this is the first case where we have linear and distinct factors in the denominator. So we'll move to the next case there, case 2, where we have linear and repeated factor in the denominator. So we'll start with one example here. So let me take, we want repeated factor. So s upon, say, s plus 2 bracket square into, say, s minus 1. So this is the fraction we are given. So we can write a first partial fraction for it, which is a upon s minus 2 plus b upon s minus 2 square plus c upon, sorry, a upon s plus 2, b upon s plus 2 square upon c upon s minus 1. Now, what is the best way for getting these coefficient here? Few of the coefficient, yes, you can get it by shortcut method. Few coefficient you can get by substitution method. You can use a combination of that also. So how it works? See here. The first thing, yes, we can get the value of b and c by a shortcut method, because when we ignore, we cannot get the value of a by shortcut method. The reason is, when we ignore the coefficient s plus 2 from the original fraction, still one s plus 2 remains there, and when we put that s by minus 2 there, we get 0 in the denominator. So the a will not work. But to get the value of b, what we can do it, just ignore the entire denominator of b from the given fractions. We're left with s upon s minus 1, where we are going to put s by minus 2. So we'll put s equal to minus 2. So we get minus 2 upon minus 2 minus 1 is minus 3. So it is a 2 by 3. So value of b we get directly by shortcut method. Similarly, the value of c we can get by shortcut method. So c equal to, just ignore s minus 1 factor. We're left with s upon s plus 2 bracket square, where we put s equal to, equate this denominator to 0. So s is equal to 1. 1 upon 1 plus 2 is 3. 3 square is 9. So the value of c is 1 by 9. Okay, already I told we can't use it for a. The reason is, if I show you here, you'll observe for a, what we have to do it, a is equal to, if we ignore this 1s plus 2 from this fraction, we left with s upon s plus 2 into s minus 1. And if we put here s is equal to minus 2, this denominator becomes 0. That is minus 2 upon 0, and that is undefined. So value of a we cannot find. Value of a we cannot find by the shortcut method. That's the problem here. So only B and C we can get it by shortcut method. So to get the value of A, there is no option other than cross multiplying and substitution. So for that, what you can do it in the original equation, you can cross multiply by the denominator s plus 2 bracket square into s minus 1. So we get one equation here, and that equation is s is equal to a times. Now yes, you can replace the value of a also here, oh sorry, b and c here. So a times first, 1 s plus 2 gets cancelled, and we're left with s plus 2 into s minus 1. So this is a into that one, plus now the value of b is a 2 by 3, so I can write it 2 by 3 here, and s plus 2 bracket square gets cancelled, only s minus 1 left, and the value of c is 1 by 9, so 1 by 9, and that s plus 2 bracket square. So this one is the cross multiplication, where we are interested to get the value of a only. And to get the value of a, see this entire equation holds for infinitely many values of s. You can replace any value of s, you will get it, other than that minus 2 and 1 values only that we already used here, s equal to minus 2 and s equal to 1, we use that. So just simple value other than minus 2 and 1 is left as a 0. 0 is the best value, or you can replace any value, say 10 or 100 also, but the best value is 0. So put s is equal to 0, you get 0 is equal to, you'll observe this is 0, this is a into minus 2, is it plus 2 by 3, not plus 2 by 3, it is minus 2 by 3, minus 2 by 3, and 2 square is a 4 plus 4 by 9. If you simplify this equation, you get the value of a. So actually just 2 is common, get cancelled, so a is equal to you can simplify and you get like a is equal to this, a I take on this side, 2 gets cancelled, it's 2 by 3 minus 2 by 9. So here is 3 by 9, 3 6 minus 2 is 4 by 9, I think. So you can check. So that about the second case, where we can get the values of constant a, b, c when there is a repeated factor. This is the case 2. Okay. Generally case 2 and case 3 are little lengthy. You already observed here, because we have to use a shortcut method as well as cross multiplication. But that is not in the case 1 and case 4, where we have linear distinct factor or everywhere quadratic term is there. So that is the simple partial fractions are there. So come to the third case, where we have linear and a quadratic factor in the denominator. So when the case 3 is there, say the example for that, say s upon s plus 1 into s square plus 4. Suppose this is the case. So the partial fraction that we have for this is a upon s plus 1 plus bs plus c upon s square plus 4. So for this case, whenever there is a one linear and one quadratic, I suggest the cross multiplication and substitution works there. That's better. But yes, few coefficient again you can get by shortcut method. For example, the value of a. The value of a, you can get it by putting s equal to minus 1 except that factor. So when you solve this, you will observe a is equal to, ignore the denominator of a, s plus 1 from the fraction. So s upon s square plus 4, where you put s is equal to minus 1. So you get minus 1 divided by minus 1 square is 1. 1 plus 4 is a 5. Minus 1 by 5. The value of a is a minus 1 by 5. Okay. Now, the remaining coefficient b and c, yes, you can do it by cross multiplication cross multiplication, that's better. Okay, that's better. So uh, so cross multiplication will be, the cross multiplication will be s is equal to a, value of a is a minus 1 by 5 into 1 upon, sorry, this is, we are cross multiplying, so s plus 1 gets cancelled, we left with s square plus 4, s square plus 4. So 1 by 5 times s square plus 4 plus bs plus c, bs plus c into s plus 1. So this is the cross multiplication. Now here, yes, you, this equation again holds for infinitely many values of s. So simplest values are, say, put s is equal to 0. If you put s is equal to 0, you will get the value of c. You will get the value of c there from this, put s0 in the above equation. That is the simplest value. Now minus 1 we already substituted, 0 we replaced here. Then you can put s is equal to, the next simple value is 1. So you can get the value of b there. So you can do that calculation, replace 0 and 1, you can find c and b there. So I will just see here what is the value of c here. So it is a 0, 0 equal to minus 4 by 5 plus c, okay, plus c. So plus 4 by 5, is it? You check, you do the step by step calculation, you get c. Once you get c, put s equal to 1 and you can get the value of b there. Okay, that about a third case. So it is again a very important method actually we require for getting the inverse Laplace. Last case, the last case is when there is only quadratic terms appear everywhere. Okay, there is no linear term in any of the place. So that is the simplest case actually, like a case one only. So whenever suppose the numerator, see the numerator is say s square, denominator is s square plus a square. So instead of a square, say I will say s square plus 9 and say s square plus 4. Okay. So in this case, the simple partial fraction works because everywhere there is a quadratic term. Nowhere the term only s appear. Everywhere s square is there. So if you replace s square by x, it looks like a simple partial fraction. So a upon s square plus 9. This is not square actually. So plus b upon s square plus 4. Okay, suppose the numerator is not there, say this is only, this is the one example. Second example, say suppose 1 upon s square plus 1 into s square plus 4 is there. That time also the simple partial fraction works, say a upon s square plus 1 plus b upon s square plus 4. So this is the second. So let I complete the first one to get a and b. Here shortcut method works. See, to get the value of a, just ignore s square plus 9 factor from the original fractions. We're left with s square upon s square plus 4, where we put s square by minus 9. So we get minus 9 divided by minus 9 plus 4 is a minus 5. So 9 by 5. Similarly, we get the value of b, and to get the value of b, we ignore the factor of s square plus 4. We left with s square upon s square plus 9, where we replace s square by minus 4. So we get minus 4 by 5. That is the value of b. So this is the first case. But if you want to see the second here, exactly same way, to get the value of a, we ignore s square plus 1. So we left with 1 upon s square plus 4 only. 1 upon s square plus 4 only, where we put s square by minus 1. Don't think we are putting some complex values or that is also allowed there. Okay, don't worry. So b is 1 upon s square plus 1, where you put s square by minus 4, and you get this a and b of the second example. So that about the partial fraction method. I hope you understood all the formulas or the methods of partial fraction, and you will perform the best in the Laplace transform. Okay, thank you.